All right, so this is the first of one or two lessons that finish off this unit. And much like the previous unit on rational equations and expressions, most of the unit was looking at a rational expression, simplifying, adding, multiplying, dividing, whatever, with these rational expressions. And just the last few lessons we're looking at working with equations where we could solve for a variable. Same sort of idea here. Most of this unit we've been dealing with radical expressions. And now we're going to use it to solve equations, and such as this. So this again is an equation. There's a left side and a right side, and we have enough information to solve for x. And so again, if I want to solve an equation, the general idea is we want to apply inverse operations to both sides. So for example, the first thing I would do is subtract 5 from both sides, just because it's easy to do, and it quickly cleans this up a bit. So I have 2x minus 1. The square root of 2x minus 1 equals 7. All right, so next, you may, if you're tempted to add 1 to both sides, well, I can't do that because that minus 1 is actually inside a square root. So let's get rid of the square root. And I think the inverse of a square root is a square, or power of 2. And so I square both sides. When I do that, again, the square root of something and a power of 2 are inverse operations. And so I'm left with just 2x minus 1. And this side I have 7 times itself, so 49. And now it's really quick. Add 1 to both sides. 2x equals 50. I can see the answer now, but I'll be showing all my steps. So divide both sides by 2. X equals 25. Now, one thing I should always do when solving a radical equation is check and make sure my answer is correct. And that's because as soon as we perform this step right here, as soon as we square both sides, we got to be careful. Sometimes we can, by squaring both sides, we end up with answers that actually aren't correct, even though we haven't made an algebraic mistake. I'll talk about that in a moment. But how do I check? It's very quick. Just now take 25, put it back into my equation, and just make sure it's true. Just make sure that 5 plus the square root of 2 times 25 minus 1 indeed equals 12. And so I have 5 plus the square root of 2 times 25 is 50. 50 minus 1 is 49. The square root of 49 is 7. And yes, 5 plus 7 equals 12. So I've checked. I know this is my answer. That's it. A really important question is, well, how on earth can you not make a mistake algebraically and get an answer that's not correct? Well, it kind of comes down to this sort of fact here. I'm going to write down something that's wrong. Negative 3 equals 3. Clearly, that's wrong. OK? And if I add a number to both sides, I'll still get an equation that's wrong. I'll get, in this case, negative 2 equals 4. And again, that's not true. Same thing if I multiply both sides by a number, divide both sides by a number, and so on. But if I square both sides, an equation that was wrong now looks correct. 9 equals 9. And so because of this fact, and notice I had an equation, I had two numbers that were different, but if I squared both, they are now the same. And I just took something that was incorrect and I made it look correct. And because as soon as we, at some point, if you at some point square both sides of an equation, there's a possibility that you're going to come up with something that's not actually correct. And as long as we check, we're good. So let's look at this one. A bit more going on. Got two x's to isolate here. One's inside a radical, one's not. I could, if I want, I could right now square both sides. This would be pretty nasty, though, to square compared to another approach. Because if I square both sides, this really means x minus the square root of 5 minus x times x minus the square root of 5 minus x. And I got a 1, 2, 3, 4 steps. And while there's a few shortcuts, it's, I don't want to do that. So what do I want to do? It's not, what I did there isn't wrong, but I think it's a little bit nicer if I subtract x from both sides. And so I have negative the square root of 5 minus x equals negative x minus 7. So now I want to square both sides. Or, to be honest, I don't like all these negatives here. So while it's nothing wrong with me squaring both sides right now, but if I just swap everything around, bring this over here and bring these over here, all my signs will change. What I'm really doing is I'm adding root 5 minus x to both sides. I'm adding x to both sides, and I'm adding 7 to both sides. That's it. in practice, I'm just swapping everything around from one side to the other, and therefore the signs change. And so I now have just x plus 7, which I like a little bit more, equals the positive square root of 5 minus x. Again, that last step there, I'm going to erase all that red stuff. Wasn't essential, but it just looks a bit nicer to me, and therefore I like it better. Now I want to square both sides. And the right-hand side is quite pleasant to work with. The square root of 5 minus x raised to the power of 2 is just 5 minus x. On the other side, x plus 7 times x plus 7 is x squared plus 14x plus 49. How did I get that? Well, you have two options. One, you could literally write this out twice. X plus 7 times x plus 7, right? We've done this sort of stuff before. And then FOIL it out. 1, 2, 3, 4 steps. And when you combine like terms, you get what I have there. Or just remember something in them we've done before in this course. Anytime you have a binomial like this squared, I know the first term, I'm just going to square to get that. I know the last term is going to be, in this case, just 7 squared. It's the middle term is always the same as this times 2. So in this case, x times 7 times 2, so 14x. And again, we did that sort of stuff with polynomials. So with that said, now this is coming together fairly nicely. I notice I have an x squared term and I have an x term. And we saw this before in the previous unit as well. This is what we call the makings of a quadratic equation. So let me add x to both sides. And let me subtract 5 from both sides. So I have a 0 on the right-hand side. And I have x squared plus 15x plus 44. And again, we've done this sort of stuff, not in a while, but if I can factor this because it equals 0, I can see my solutions by inspecting my factors. And I can factor this quite nicely. Two numbers that add to 44, that add to 15 but multiply to 44 are positive 4 and positive 11. Those are my factors, which means now by inspecting my factors, I can see one of my solutions seems to be negative 4, and another solution seems to be negative 11. But let me check now. Because again, as soon as I did this step right here, I run the risk of one of these solutions, or maybe both of them, not actually working. Okay, so all I got to do is check. So going back so I can see everything here, first let me check with x equals negative 4. So I have negative 4 minus the square root of 5 minus negative 4. And that should equal negative 7. Let's see, I have negative 4 minus the square root of 9. 5 minus negative 4 is 9. So I have negative 4 minus 3, and that does equal negative 7. So I know negative 4 is good. And then let me check when x equals negative 11. So I have negative 11 minus the square root of 5 minus negative 11. And that should equal negative 7. So I have negative 11 minus the square root of 16, which is negative 11 minus 4. And negative 11 minus 4 does not equal negative 7. Negative 11 minus 4 equals negative 15. Which means this is not one of my solutions, so I need to reject it. We call this an extraneous solution. And we saw this a little bit in the last chapter as well. And so that means in the end, x equals negative 4 only. And like I said, as soon as you perform this step right here, where you square both sides, it doesn't mean you will have an answer that's wrong, you have to reject, but you open up the possibility of that happening. And so, let's look at one more example before our final problem. So again, I want to solve for x. And so I have a lot of options. The first thing I'd like to do is just add x to both sides, so that on one side I have just a radical, 7x minus 54 in the square root, and on the other side I have x take away 6. Because now if I'm going to square both sides, and again as soon as I do this, I open up the option that I may have to reject a solution. As soon as I do this, the left-hand side is quite nice. It's just 7x minus 54. The right-hand side, again, if we just think about, come back. If you think about the work we did a lot in the previous unit, I can do this quite quickly as well. I know it's going to be 3 terms. It's a binomial that I'm squaring. The first term is going to be x squared. The last term is going to be 36. Negative 6 times negative 6. The middle term is going to be x times negative 6 twice. So negative 12x. So again, that, same as that. Okay, and then like before, I have the makings of a quadratic equation. I want to make everything equal to 0, so I'll bring everything to the right-hand side, since my x squared already is positive. So in doing that, I'm subtracting 7x from both sides, and I'm adding 54 to both sides. So if I do that, I get 0 equals x squared minus 19x plus 90. All right, and again, if I can factor this, I can inspect my factors, and I can see my solutions, but then I just want to check. Two numbers that multiply to 90 but add to negative 19 are negative 9 and negative 10. And so by inspecting my factors, I can see pretty quickly that this factor must lead to a solution of x equals 9, and this factor must lead to a solution of x equals 10. So right now it looks like I have two solutions, again, 9 and 10. But now let's just check and see if they work. And again, take each of those and put it back into my equation up here. And so, for example, if I check with x equals 9, I have the square root of 7 times 9 minus 54 minus 9 equals negative 6. And so I have the square root of 63 minus 54 minus 9, which is the square root of 9 minus 9, which is 3 minus 9, which equals negative 6. Yep, that works. And then do the same thing with 10. And I will, instead of boring you even more by watching me plug a bunch of numbers in, I will say 10 works as well. If you put 10 in, if you replace all the x's with 10, the left and right side work, which means both of these work, which means this equation has two solutions, x equals 9 and 10. Like I said, don't assume one will work, one won't work. Don't have to assume anything, just check. All right, that leads me to my final problem, where I have a formula here that relates the thickness of a piece of lumber to the mass that it can support without breaking. So m is the mass in kilograms, t is the thickness in centimeters. That said, lumber is usually measured in inches. So a piece of lumber is 4 inches thick. What mass can it support without breaking? Well, for this, we need to kind of know what's 1 inch in centimeters. Now, that's not actually a competency of this course, so if you're not sure what 1 inch is in centimeters, that's okay, even though we probably should know the connection between inches and centimeters. It's about 2.5. Since these are different measurement systems, it's not exactly 2.5, it's pretty close, and so therefore 4 inches is about 10 centimeters. And again, we live so incredibly close to the United States that so much of our infrastructure is still based in imperial measurements. It's kind of good to know inches is about 2.5 centimeters. And so now I take my equation up there, and the thickness is 10 centimeters. So 10 equals 1/5 times the square root of m over 3. And now we can solve for m because we know t. All right, so how would I approach this? First thing I would do is multiply both sides by 5 to make that 1/5 kind of cancel out. So then I have 50 on one side equals just the square root of m over 3. And again, there's always options. The next thing I would do is square both sides. And so I have 50 times 50, which is 2,500 on one side, and just m over 3 on the other. And then lastly, multiply both sides by 3. And so I have 7,500 equals m. I've solved for m. And m is the mass in kilograms, I think it was. Yep. So the answer is about 7,500 kilograms. It's a lot. All right. And then again, I guess I should say I should check, but I can check pretty quickly. If I just put 7,500 right there, it will equal 10. But yes, I really should always check. But it works, so I guess I checked. All right, so before I end this, the last lesson is the same idea, just slightly more complex equations, but same idea. So make sure we're always checking when we're solving these. Shouldn't take long, but we always want to check as soon as we've squared both sides.